Hi class, in this lecture we continue our study in chapter 12 by moving into section 12.3, which is called the dot product. And this is just a mathematical operator working with vectors. So far we've added two vectors and multiplied a vector by a scalar. That's what we did in the previous section. So the question arises, is it possible to multiply two vectors so that their product is a useful quantity? It turns out yes. One such product is what's called the dot product, whose definition is just as follows. So here I have a three-dimensional vector A given by the components A1, A2, A3, and a three-dimensional vector B with the components B1, B2, B3. Then the dot product of A and B, okay, is the number, and we denote it as A times B, just like that, given by the following. Vector A dot product with vector B, all you do is you multiply their corresponding components, so A1 times B1, A2 times B2, A3 times B3, and you add them. So thus, to find the dot product of A and B, we multiply corresponding components and then just add. Note when you do this, you're just going to get a single number as your answer. All right, so it's important to note that the result is not a vector. Okay, it is a real number. That is, it's a scalar. And for this reason, the dot product is sometimes called the scalar product, or it's also even referred to as the inner product. So although that first definition is given for three-dimensional vectors, the dot product of two-dimensional vectors is defined in a similar fashion. Again, you're just not multiplying by the z component. And forgive the little typo here. This should just be multiply. So you could be multiply a1 times b1, and then you'd add it to a2 times b2. Let me just do a quick example here. I'll do a bunch of them actually. So I have the vector 2, 4, and I'm dot producting it with the vector 3, negative 1. So you just go 2 times 3, 4 times negative 1, and you sum those. That would be 6 plus 4 gets you 2. Similarly, if you have a three-dimensional vector, first vector A is negative 1, 7, 4. The second vector is 6, 2, negative 1 half, and you want it to find their dot product. Just multiply the corresponding components. Negative 1 times 6, I would add to that 7 times 2, and I would add to that 4 times negative 1 half. That would just get you 6. Okay, this one here, notice that they're trying to trick you on this one. This is a three-dimensional vector with the ijk notation times 2j minus k. Notice how there's no I in this second vector here. That just means they have 0 I. Excuse me. So the coefficient in front of this one would be 1 times 0, and then it would be 2 times 2, and then negative 3 times negative 1. You would sum all those, and you would end up just getting 7. Okay, so the dot product obeys many of the laws that hold for ordinary products of real numbers. These are stated in the following theorems right here. Theorem here. This is just properties of the dot product. So just if A, B, and C are vectors, and C is a scalar, A, B, and C are vectors, excuse me, and C is some scalar constant. Notice this one's not bolded. All these following properties would hold. And this is exactly like the same type of properties of the product that you would think when working with real numbers. They also apply for vectors here. Okay, so these properties are easily proved using definition 1. For instance, you can see the proof here for properties 1 and 3. Very, very easily worked out. So all these properties hold. Okay, so the dot product A and B can be given a geometric interpretation in terms of the angle theta between the two vectors A and B. So if here's vector A and here's vector B, we want to now talk about this angle theta between these two. So this one right here. All right. So which is defined to be the angle between the representations of A and B that both start at the origin. Okay. And this is going to be where theta is bound between 0 and pi. Okay. So theta is going to be in radians here. So in other words, theta is the angle between the line segments of the vector OA and OB here. All right, in the same figure. Note that if A and B are parallel vectors, okay, then either theta would be 0 or pi in this case, because they'd both be emanating from the origin. In this case, they'd either be overlapping each other if they were parallel, or their directions would be opposites of each other. Okay, so the formula in the following theorem is used by physicists as the definition of the dot product. Okay, so if theta is an angle between the vectors A and B, then the dot product, so A dot product with B, okay, will always be the same as, okay, going back, this dot product here will end up being the same thing as the following. The magnitude of A times the magnitude of B times the cosine of theta here. All right, so if the vectors A and B have lengths 4 and 6 and the angle between them is pi over 3, let's find the dot product A and B just using this theorem right here. All right, so using theorem 3, we have the following. Dot product A times B. Here I'm telling you that they have lengths of 4 and 6. Okay, so I'm telling you this and this for the corresponding vectors right here. And then I'd multiply that by cosine of the angle between them, which would be pi over 3. So you would have 4 times 6 times cosine of pi over 3. Well, we know cosine of pi over 3 is 1/2. So 4 times 6 is 24 times 1/2. That's how they got the 12 here. All right, the formula in theorem 3 also enables us to find the angle between two vectors. So here's a corollary. If theta is the angle between the non-zero vectors A and B, then cosine of theta would be equal to A dot product of B divided by the distance of A times the distance of B. So you can see here, the lengths of A and B, my apologies. You can see here to find cosine of theta in this, we're just dividing this A and B part over here. All right, so let's find the angle between the vectors A, which is given by 2, 2, and -1 as its components, and vector B, given by 5, -3, 2. Okay, so this is a three-dimensional vector. So the first things we have to do is figure out the magnitude or distance or length of each of these vectors. So the magnitude of A, using the formula from the previous section, ends up being 3. Magnitude of B ends up being the square root of 38. So we've got these two parts here, okay? So we've got the denominator right here. Now we just need to find the dot product here for the numerator part of this. And so this would be 2 times 5 plus 2 times -3 plus -1 times 2. And it looks like the dot product or the inner product here is just equal to 2. So then what we see here is cosine of theta is equal to the dot product of A and B divided by the magnitudes of A times B, which ends up just being 2 divided by 3 square roots of 38. So here to get cosine by itself, obviously we just take the inverse cosine of each side. And if you were to plug this in your calculator to get this, this would be roughly 1.46 radians or 84 degrees. Okay, so just a few other things real quick about this. So two non-zero vectors A and B are called perpendicular or orthogonal if the angle between them is a 90-degree angle, pi over 2. So then obviously this states dot product of A and B, if they're perpendicular, this has to be equal to 0, right? Because cosine of pi over 2 is 0. And conversely, if their dot product is equal to 0, then either then cosine of theta equals 0. So obviously then the theta has to be pi over 2, and the 0 vector is considered a perpendicular to all vectors. Therefore, we have the following method for determining whether two vectors are orthogonal, okay, or if they're perpendicular. Two vectors A and B are orthogonal if and only if their dot product is equal to 0. So if you take the dot product of two vectors and it comes up to be equal to 0, you know that the two vectors are perpendicular to each other. All right, so for example, let's show that 2i plus 2j minus k is perpendicular to 5i minus 4j plus 2k. So all you have to do is find the dot product of these. So you take 2 times 5 plus 2 times -4 plus -1 times 2. If you were to work this out, you would see that it would be equal to 0. So what you can say then is these two vectors are perpendicular, all right, because their dot product is equal to 0. Okay, so because cosine of theta is greater than 0 if theta is between 0 and pi over 2, and cosine of pi over 2 is less than theta, less than or equal to pi, we see that A dot product of B is positive when theta is greater than pi over 2 and negative when theta is less than pi over 2. So we can think of A dot product of B as measuring the extent at which the vector A and vector V point in the same direction. So the dot product of A and B is positive if A and B point in the same general direction, like you can see here. That means the angle between them is acute. 0 if they are perpendicular and they point in opposite directions, okay, if the angle between them is obtuse. Okay, that's what we're saying here. So like in this example here, because the angle is 84 degrees here, we can say that they point in the same direction. All right, in the extreme case where A and B point in exactly the same direction, we obviously have that theta is equal to 0. So cosine of theta is equal to 1. And in this case, the dot product is equal to the product of the magnitudes here. So if A and B point in exactly opposite directions, then obviously we have theta is equal to pi. And so cosine of theta is equal to -1. And the following will hold. All right, class, I'll pick this up with some more examples, or part 2 for this section in the next video.